Welcome. This screencast is about functions and what a function is and how we represent a function, and all of that will be important for us as future elementary educators as we look at how patterns and structures lay the foundation for some algebra. Most people think about functions as a rule. There's an input into the function, there's some rule that turns it into an output, and the result is the output. It's a rule. It's a way we assign inputs to outputs. And that's a very elementary way to look at functions. Other ways that some people look at functions is as a machine. So this is the function machine, and let's say that this function doubles and then adds 1. Let's say that that's what the machine does. Inputs go into the machine, outputs come out of the machine. So if 5 goes into the machine, double, add 1, 11 comes out of the machine. If 7 goes into the machine, then double, add 1, 15 comes out of the machine, and probably more importantly, if x goes into the machine, then 2x plus 1 comes out of the machine. We would write this function as f of x equals 2x plus 1. These parentheses do not indicate multiplication. It is a function notation. F of x equals 2x plus 1. And then we would say things like f of 0, if 0 is the input, then the output is 2 times 0 plus 1, that's 1. If 2 is the input, if 2 goes into the machine, then f of 2 is 2 times 2 plus 1. That's 5. So, side note here, uh, we talk about the domain of a function. The domain is the set of all inputs. So anything we could possibly put into the machine, we take that entire collection all together, and that collection is the domain. We also talk about a codomain. The codomain is the set of all possible outputs. So in this case, inputs are numbers, so we would say that the set of whatever kind of numbers we want is the domain. Maybe we want the set of all real numbers to be the domain. The codomain would be the set of all possible things we could expect to come out of the machine. But not everything always comes out of the machine. Maybe you expect that any real number could, but not every real number does. The range is the set of all actual outputs. So the range is a subset of the codomain, but it is not always the codomain. Now, sometimes we represent functions as machines, and sometimes we represent functions with arrow diagrams. Put the domain over here, we put the codomain over here, and maybe we have 0 and 2 and 5, and maybe double plus 1, double plus 1, double plus 1, and we indicate that 0 maps to 1, 2 maps to 5, 5 maps to 11 with arrows. This is the function f. It sends 0 to 1, it sends 2 to 5, it sends 5 to 11. An arrow diagram is a great way to express a function, particularly if the domain is finite and the codomain is finite. It is less good if the domain and codomain are infinite, because it's harder to see infinitely many arrows than it is to see finitely many arrows. Other ways that people show functions is in a very familiar table form, where we would have 3 and 5 and 12, and then we'd double add 1, double add 1, double add 1. We can express functions in table form. When we express functions in table form, or even when we use the arrow diagrams, really we're thinking about 3, 7 as an ordered pair. This is an ordered pair because it's a pair, and because there's an order that matters. Input, output, X, Y, element of domain, element of codomain. When we express functions in any of these forms, we're thinking about ordered pairs. The ordered pairs are obvious here. The ordered pairs are obvious here. 0, 1, 2, 5, 5, 11. The ordered pairs are even obvious here because the inputs are the first coordinate and the outputs are the second coordinate. Now, not everything in the world is a function, but lots of things are. Oh, nope, too far. One other way we show functions like this is in graphical form. There's an x-axis and a y-axis, and we can think about some of our ordered pairs, right? We had some ordered pairs. One of the ordered pairs was 0, 1, so there's 0, 1, and one of the ordered pairs was 2, 5, there's 2, 5, and one of the ordered pairs could have been like 1, 3, double and add 1, and if we took all the possible inputs, all of the possible real numbers, we would get something that looks like this. All of these represent the same function. They all represent the same function. Now, not everything is a function. For example, if we had a scenario where there was 1 and 2 and 3 here, and there was maybe 4 and 5 and 6 here, and the arrows went like so, we would recognize that this input goes to two different outputs, and functions don't work that way. Back to the machine analogy. When a number goes into the machine, only one element comes out of the machine. So one input has to lead to one output. So in this particular case, this is not a function. In table form, we would have 1 going to 4, 1 going to 5, 2 going to 5, 3 going to 5. We would have one input going to two different outputs. It is not a function. This is not a function if one input goes to more than one output. It is perfectly acceptable for multiple different inputs to have the same output. That's perfectly acceptable. But one input leads to one output. That's how the machine works. Okay, I hope this is helpful to illuminate some of the things you were reading about, bring back some memories from a long time ago. We'll do a second screencast with some examples of functions in various forms in case this is not quite sufficient.